anyway, I'll start with unit 1. Okay, and unit 1 is basically your special theory of relativity. Okay, so we'll start with the special theory of relativity, and as I told you, I will go a bit slow. Okay, we are not going to go too fast. Preferably we'll try to understand the topic as well. Okay, and eventually we will try to share some videos, some content, because we have an online class, so we can have some relevant content on screen, some animations and all. That will always help. So the term relativity is something which you might have already done, okay, or you might already know. Okay, and we will basically just start with this. Let's imagine that there are some things which are called frames of reference, and that's very important when we actually look into a concept. Okay, we basically have it here. Okay, and these are nothing but called frames of reference. So the idea of frames of reference is something which you might have already done in your lower classes, but then we are going to uh, base on this particular idea when we are going to study special theory of relativity. Before we start with special theory of relativity, or what's the difference between special theory and general theory of relativity, okay, we have to just consider one fact. What is the word? That's relativity. Okay, what's relativity basically? So whenever you are, let's say, in a moving bus, okay, or your friend is in a moving bus, and you are on the ground, and the bus is, let's say, moving with a velocity v. Your friend has a velocity with respect to you. Okay, he may be moving inside the bus, and if the bus velocity is v, these will actually affect by way you are actually looking at your friend, because there is a motion which is involved. But if you are also in the bus, your friend is also in the bus, basically the relative velocity is more or less zero of you with respect to your friend. Okay, so this is what is relativity is all about, and here we see that there are actually frames of reference that we need to understand. So the bus may be one frame of reference, and if you are on the ground, that may be considered to be the second frame of reference. So this is the first frame of reference, this is the second frame of reference. So a basic idea of frames of reference, we already have it. We just need to put it in words, or maybe a mathematical idea for it. That's very important. Okay, so relativity or special theory of relativity or Einstein's idea of relativity are some very interesting topics which actually has been generating interest for a very, very long period of time. So when we'll go through these units and chapters and topics, okay, we have to understand the story behind these. Okay, that's important, and that will actually generate that interest in us. For example, when Einstein was actually working on this, general theory of relativity, and then eventually he came up with special theory of relativity, everything became so interesting that it started to explain whatever phenomenon were happening in and around us. You imagine, something like time travel today, or maybe the what happens to your age when you're moving at a very fast speed. Okay, or maybe you are considering something like a spaceship, and you're observing some length in that spaceship. The length keeps on changing depending on from which frame of reference you're observing. Okay, these ideas were not there in 1800s. In 1900 it came up, and today we can also imagine something about time travel. Movies are being made on that. Okay, so every idea is based on this special theory of relativity. So when we talk about special theory of relativity, okay, a basic idea, or we will start with these simple things. As I told you that I'll keep on giving you these notes. Okay, so if I give you the notes, it will be easy for you to follow it, and you don't need to refer to too many books. So if I just go for the first basic idea, time is different in spaceship. Okay, so imagine you are looking into a space mission. Okay, and there is a spaceship which is being launched. Okay, and time would be different in the spaceship at different points. Okay, at, let's say, I'll just give you a basic idea of this, at different points when observed from outside, at different points when observed from outside. So we'll start with straight away with this. Okay, let me tell you something very clearly, that we do have the syllabus, and I will try to cover, or in fact we will cover all the topics, but then it may not be in sequence, because I need to clear the basics first, and then only we can go to the topic which I basically mentioned. So maybe this is a spaceship. Okay, and maybe you are trying to observe it from Earth. Okay, maybe this is the Earth, and then you are actually trying to observe it from the Earth, and you observe a point here, some event here, you observe some event here, and you observe some event here. And this spaceship, it's basically moving with some kind of velocity v. Your observation basically may not be the same when you observe it from Earth 4.1, 2, or 3. They all may be more or less different, varying in time. Okay, if there is a length, there might be some change in difference of length also. Okay, and this is actually coming under the scope of special theory of relativity. Okay, this is very important. So what we are going to do is we are going to just write down few bullet points. Okay, this is the first thing that we should understand. The second thing would be time and space are not absolute. Time and space are not absolute. What does it mean? It depends what will be the time or in what space you are from the frames of reference. If you are observing it from different frame of reference, the time might be different. Okay, if you are in the same frame of reference, the time will be different. Okay, so if you want to measure the time, okay, when you are in spaceship, or if you want to measure the time when you are on Earth, both might be different. So they are actually not absolute. So if I ask you a question that, what is the basic points that we should note when we're talking about special theory of relativity, okay, this was the basic idea here. Time and space are not absolute. Okay, one more important point is this, which is, usually mentioned, but then we don't put much importance to it. If you have read about relativity, it applies to linear motion. Okay, it applies to linear motion. Now what does it mean? It means that if we are considering, let's say, an object which is, let's say, of length L, okay, on Earth, we may be observing it as length L, okay, because we are measuring it on Earth itself. Now let's say that particular object has started moving into the space and it is moving at a very fast speed. Then we are going to observe something which is called length contraction. Eventually we are going to study about length contraction later. And then that length, since contraction, I hope you understand, it will be a new length L dash, which will be shorter compared to the original length if you are measuring from the Earth's frame of reference. Okay, but this motion that we are talking about is linear, so it's basically going in one particular direction. There is no two-dimensional motion. Okay, it's not going along x and y axis, it's not following a curved path, it's not following a circular path or a spherical three-dimensional path. It's basically just going in one linear direction. Okay, so that's very important. So special theory of relativity, you have these points that we should note. Okay, so so what does it mean that, if I have a motion which is not linear, can't we apply relativity? We can do that, but then that will become a complex problem, and there we need to use general theory of relativity. Okay, so in general I can say, for more complex movement, okay, we need general theory of relativity. Okay, so that's important. General theory of relativity. So in general theory of relativity, it is more complex in the sense it might not be a linear motion every time. And when we talk about special theory of relativity, don't include the terms like acceleration and all. Okay, so that means we are not including gravitational effect and all. That's the special theory of relativity. So eventually you can understand that getting a concept of special theory of relativity is relatively easy compared to general theory of relativity. Okay, etc. Let's say. So in general theory of relativity, we have inclusion of these terms: gravitation, the non-linear motion, and so on. Okay, so it becomes more complex system. So at this point of time, okay, you're doing a BTech course, we are not really going into the general theory of relativity. Our study will be mainly focused on special theory of relativity. Okay, we're going to know the difference between general theory and special theory of relativity. Okay, and which is not very complicated. I hope by now you understand that when we talk about something like inclusion of acceleration, we're going into the general theory of relativity, which might be more useful because there are more, uh, events around the world or the universe or in space where there is acceleration involved. But then there are also events which has got a constant velocity involved. So if we have constant velocity, we are talking only about special theory of relativity. So as I said, we need to know the axis system, and considering that this is important for the basic understanding, we are just going to discuss a bit on the axis system. Okay, let's talk about the axis system. And when we actually know about axis system, whenever you are going to draw it, okay, I hope we already know these things. Okay, we are just going to consider everything in a three-dimensional space. Okay, and depending on the convenience, we are just going to say, let's say a body is moving along the x-axis or along the y-axis. Okay, it depends on what kind of problem we are solving. But then this is the basic idea of axis system which we already have. Okay, and then this would be nothing but this is your x-axis, this is your y-axis, and this is your z-axis. Okay, so in axis system what we know is the length or the distance, everything is basically known to us. So in general, in axis system what we prefer is knowing the length. So maybe a body is moving and we are talking about length contraction. If you're basically having this much of length, we know that it's along the x-axis. Okay, and if you're making it an angle, we have to resolve it into your components along the x-axis and the y-axis. Okay, if you're considering a vector quantity, let's say velocity. Okay, and so on. So basically here what we're going to do is, let's say I'll just put one simple example, knowing the length. Okay, knowing the length scale. Okay, let's say knowing the length scale to find position. So if you want to find out the position of a particular point, we have to know what is the length scale. So that means along x-axis what is the distance and so on. Okay, so if this particular length, now if you are in this particular frame of reference, let's say you are inside the bus and the bus is moving very fast, and you have a stick or a scale inside the bus which is also moving with you inside the bus, right? So both the scale and you are in the bus. So the bus may move at a very, very fast speed. You are still going to observe that the length of the scale does not change. Okay, so that means with respect to that frame of reference, okay, if you understood this example, if the length, okay, does not change with time, does not change with time, it is at rest. It is at rest. So asking it to a layman, okay, and not to engineers or who has studied physics, that okay, you are inside the bus, a scale is there and the bus is moving, will it be at rest? And then he might say no, it won't be at rest because the bus is moving. But it depends from which frame of reference you are observing. Since you are observing it from the bus itself, it will be at rest. But if you are at the ground and the bus is moving and the scale is there, it won't be in rest. Okay, so that's very important. Now, what is this frames of reference all about, and which frame of reference are we going to consider? Okay, so frames of reference. Maybe I'll take this here. Frames of reference. Okay, so frames of reference, if I say, let me just, take one example. What will frames of reference do? It will tell me the position of an object. Right, that's the important rule of frames of reference, position of object. Okay, so if I want to know the position of the object, I basically have to know what is the frames of reference, and there are two types of frames of reference that we should know. Okay, and maybe we can just make this. Okay, so what are those frames of reference? One is inertial. Okay, one frame of reference is basically inertial. So it is slowly building up towards the topic that we are going to concentrate more, and the other one is non-inertial. Okay, so inertial, non-inertial, it's not very difficult to understand if you know the basics of physics. In the basics, we know when we start with physics, we do say the Newton's laws. Okay, so Newton's law, it is valid, but there are certain conditions in which the Newton's law may not be valid. I'll give you some examples here. Okay, so if we talk about Newton's laws, now this is important. Okay, and let's say I'm talking about the first law here. Okay, first law. The first law, that is, if F is equal to 0, then A is equal to 0, right? We already know it. If F is equal to 0, then A is equal to 0. Now what does it mean? If F is equal to ma, we already know that's the first law. And the first law says that, whatever object you have will be in its rest position until and unless you actually apply an external force to it. Okay, so if you don't apply an external force, there is going to be no acceleration as such, and as a result F will remain as 0 if A is equal to 0. Okay, now this law, that is the Newton's first law, may or may not work in all frames of reference. Okay, so that's very important. So there is something which is called a pseudo force, that is also very important. So what I can say is Newton's first law, okay, or in general, let me just say this, Newton. So this is important for your notes. If I ask you the difference between the inertial and the non-inertial frame of reference, maybe you can take help from this particular slide. Okay, so Newton's first law may not work in all frames, may not work in all frames. So first thing, that's the first thing to note. Okay, now if I give you an example for this, which frame it won't work. Now you are in a moving bus. Okay, you are in a moving bus. Okay, and the bus suddenly stops. Okay, what will happen? Because of inertia, you will be moved forward, but there was no direct force acting on you at that particular moment. Okay, so example, maybe inertial force in a moving bus, inertial force in moving bus. So that force will be there, and then the force won't be directly on you. So this is an example, okay, of a non-inertial frame of reference. Okay, so if the laws works in a particular frame of reference, that will be an inertial frame. Okay, so maybe I'll just come to the final definition here. So if I ask you the question, then what is the difference between inertial and non-inertial frame? Probably this is the most important sentence. So in frames where, okay, Newton's first law work, first law work is inertial frame. Okay, so please write it down, and you'll see that whatever system we are going to consider, you are going to get only this inertial frame. Mostly we are going to talk about inertial frame. Even if someone asks you a question, okay, you're doing your engineering at the end of the course. Obviously, you're going for placements and all, and there these things are more or less basic questions. If you have a course on physics, okay, you should be able to know these things. So these things may be a bit important from that point of view also. Okay, and where the first law doesn't work, where first law does not work, is non-inertial. So you cannot directly invalidate Newton's law. Okay, it's there, the force is there, but then that force is not acting directly on you. It's an inertial force that we are talking about here. Okay, so in a moving bus, so first law does not work as non-inertial frame. So the good thing about this is we are just going to talk about inertial frame most of the times in this syllabus. So include a non-inertial frame, include acceleration, the system or the study that we are going to do will become more and more complicated. Okay, so since we are talking about a force, we really don't see that it's working directly. What is that force called? That is actually called the pseudo force. So you might already know about the word pseudo. Okay, something which is giving you that effect, but still it's not there. Okay, that is called pseudo. So I'll just write this down as pseudo forces. So we have to do that, building up. Before we really go or jump into the derivation part, we should know and be very clear about all these definitions. Okay, pseudo force. So what is this pseudo force? This is a force, no doubt, because even if we are talking about a non-inertial frame of reference, you have to analyze that system. So that means if you want to analyze that system, you want to write down an equation for the system. You need to know what is the force, you need to know what is the acceleration. For that, we need to consider a force. If you don't have a force, we cannot really write down an equation of motion. Or if you don't have an acceleration, we cannot write down an equation of motion. So this inertial force that we're talking about is something which is pseudo force, which is considered in order to have a mathematical approach to such system. So that is pseudo force. Okay, so we use such forces, that is the pseudo force. Okay, such forces in a non-inertial frame, non-inertial frame. Okay, why we use that? So that we can use, so you can easily make your notes from here, and I don't mind you taking a screenshot and keeping it with you, but then eventually if you forget, then there is no point in taking that screenshot, right? You can always do that, but then I'd prefer you writing it down in your own handwriting so that you remember it better. Okay, that can only be an advice in that frame. So if you want to use Newton's law in a particular frame, we are basically going to use this idea of pseudo force. Okay, I can give you some examples of pseudo force. Let's say you are basically having let's say a jar. Okay, and then you manage to tie a thread here, and let's say hang a ball here. You have a ball which is hanging inside this jar. Okay, and then maybe the ball, or you are applying a force. Okay, maybe you are applying a force in this particular direction. Okay, in this particular direction you are applying a force. Now if you apply a force in this particular direction, the ball will actually tend to move in the opposite direction. Okay, so the ball will actually tend to move in opposite direction. So that's the force that is basically acting on it. Okay, and this force that we are actually talking, which is acting on the ball, is actually the pseudo force. So this is a good example of pseudo force. So if you want to analyze the motion of this ball, you are going to use this concept of pseudo force. This is how our syllabus is designed. Okay, this is how the ideas develop. In your lower classes, maybe when you're in school and all, okay, we really don't talk about pseudo forces. We say that there is a ball inside a jar and the force is being applied. We know that the ball will move in the opposite direction, which is an inertial force. So we know it's also a force, but there we don't talk about pseudo force at all, because there we are not dealing with relativity or non-inertial frame or inertial frame. Okay, so that's important. But what we are going to do in this syllabus, that means in special theory of relativity. So most of the times you just type STR in Google and you see that the full form is special theory of relativity. What we are going to do is we only discuss the inertial frame, the inertial frame. Okay, so before we proceed, okay, one of the points that we have seen here is very important, that our syllabus is on STR, right? We are going to talk about constant velocity, because we are not going to talk about gravitation and all. Constant velocity and linear motion. So it makes our job easy to understand the topic, since we are not going to talk about general theory of relativity. It's going to talk about special theory of relativity, special case. What's the special case? The velocity is constant and the motion is linear. Okay, and then finally we are just going to talk about the inertial frame. It makes things even easier. We're not going to talk about the non-inertial system. Okay, so that's the the build up to the syllabus, so that we can understand this better. Okay, so that's very important. So let's just try to understand something, when we're talking about two frames of reference, and let's say two, they are moving with respect to each other. What are the changes in velocity? What are the changes in position that we should know? And that would be on, something which comes under Galilean transformation. Okay. So the topic is, the title of the topic is frames of reference and Galilean transformation. So every now and then you will be coming across these big jargons in special theory of relativity, okay, or eventually in any topic that you're going to learn in this syllabus. So these are all jargons, but if you understand it, kind of these are simple. Transformation, not very difficult. You have a body in one frame of reference, you have motion in another frame of reference. If you want to connect these two frames of reference, you usually say it's a transformation equation. Okay, and Galilean has given this idea, Galileo, so that is Galilean transformation. So we have to understand that, but before we do that, okay, let me just draw two frames of reference which will make the picture a bit more clear. Okay, so let's say I'm just considering a two-dimensional motion right now. You can also draw the third dimension, the z-axis, but then we are not going to really consider any kind of motion along that particular direction. Okay, so we have this here. Let's say this is one frame of reference, and this is another frame of reference. I would just like to tell you the notations. Different books might be using different notations, but then most of the times it is actually the primed frame and the unprimed frame. Two reference frame you are comparing. Okay, so one maybe origin would be O, and the other one would be origin would be O prime. And these are two frames of reference. Okay, and they are given a particular name. Okay, so maybe I will just use this, and throughout the syllabus we'll try to use this frame reference as, let's say this is frame S, and then this, okay, this is frame S prime. Okay, and what happens here is this is your x-axis and this is your y-axis. Okay, just can you give me a moment? An important call coming in, just a sec. Okay, so you have this frame S, and then you basically have got this frame S dash, okay, S prime. So what happens here is if this is x and y axis, this would be your x prime and this is your y prime. So many a times I'll tell you that this is the primed coordinate system and this is the unprimed coordinate system. Okay, so you have to understand that the x and the y axis may be different. Okay, and what we are going to do is we are going to say that this second frame of reference, which is the primed coordinate system, is moving with a velocity v. This is very important. This is very important even if you're imagining that someday time travel will become possible. Okay, at this point we can't say and we don't know, and it might not happen because of the existence of mass and Higgs boson and all, although this is out of the scope of the syllabus. But then still I'd like to tell you that why time travel is very difficult, because of the mass that we have. So we are going to talk about mass also, okay, relativistic mass. If you move at a very fast speed, your mass is eventually going to grow. Okay, you're going to gain more and more energy. Any system cannot have an infinite amount of energy, and that kind of restricts us from time travel at this particular point of time. But then if there is a velocity and if there is a frame which is at rest and there is another frame which is moving with a velocity v, for example, you are standing on the ground, so you're in the rest frame O frame or the F frame S, and a bus is moving with your friend inside, so that's the primed frame and that is frame S prime. Now, is there any relativistic effect between you and the bus? That depends on what, with what velocity the bus is moving. If this velocity is very high, let's say comparable to the speed of light, you are really going to feel that effect. On the other hand, if this velocity is not very high, maybe something like which we observe in our general day-to-day life, maybe 140, 150 kilometers per hour, you are eventually not going to get any kind of special theory of relativity effect. It's there, but it's negligible. In fact, if you have a supersonic jet, okay, which moves at the speed of sound, okay, maybe around 3000 meter per second and so on, even that also is going to have a very minor effect, okay, relative effect. So we are going to do some numericals to understand that, okay. So before that, let's just try to understand these frames of reference. So obviously not today. Today is, I think we won't be doing any numerical. So let's just write down few points here also. If, okay, we are trying understanding frames of reference here, okay. If S dash moves with uniform velocity, see whatever I said, I'm just putting it in sentences, with respect to S, right? So this S dash is moving with uniform velocity with respect to S. Nothing in this space is at rest. It only depends from which uh, you know observations or which point of view you are observing it. Okay, so nothing in space is at rest. So this space and time is absolute is a wrong concept. It's not absolute. That's very important. Okay, so this S with velocity with respect to S, okay, and this is also inertial. Okay, so we can say that then S dash is also inertial. Why I'm writing this? Because you might say that the second frame of reference is moving. Is it an inertial frame or a non-inertial frame? This is inertial frame because it is moving at a constant or uniform velocity with respect to S. So that means this system as a whole, which system? If we include a system of frame S and frame S prime, include them together, both of them is actually a inertial system. Okay, so that's very important. And then for ease of calculation and convenience, so that we don't involve too much vectors in it, no angles and all, okay, this x and x dash, okay, that means the frames or the x-axis of these frames are on the same line, are on the same line. So these are some important points that we should note before we can actually do the Galilean transformation. Same line. Do they need to be in same line always? If they are not in the same line, can we say that something is different? No, it's the same, but then the calculation will become a bit more complicated. So what we are doing is we are considering it. We are saying that they are in the same line. Consider. Okay, that's it. Okay, second point. And we also say that there is no motion along y and y dash. So maybe y dash and z dash coincides. What does it mean? You see, there is a motion along, it's possible that there might be a motion along y-axis, or it may be having a motion along the z-axis. So z-axis may be out of the plane or inside the plane, y-axis may be up or down. But here what we are saying is that the motion is only along the x-axis. So it doesn't wobble, it doesn't go up and down, it doesn't even come out of the plane, okay, or go into the plane. Okay, so there is only motion along the x-axis. So that is the consideration that we are basically doing. Okay, and what happens here is, for understanding Galilean transformation, when this O and O prime are at same point, so what does it mean? Let's say I'm dragging it behind and it has not yet started. Okay, so maybe there is a racetrack, okay, and there are two persons who are going to race. Eventually at time t is equal to 0, both of them are at the same point. Okay, and let's say somehow as soon as the race starts, this person, this athlete, starts moving with a velocity v, and this athlete does not move. Okay, maybe he's nervous, he doesn't move. So this might be that kind of situation that we are talking about here. Okay, so what happens is at t is equal to 0, both are going to start from the same point. So that means when O and O prime are at the same point, we have got the time in the unprimed frame is equal to the time in the prime frame is equal to 0. So it's the beginning of the event. Okay, so that means this is the point where this O prime will actually be crossing O. Okay, O prime crossing O. So this is important. Okay, so I hope you understand this. This is a very simple idea. Okay, so what is happening here is we're basically going to have two events here. Okay, one event. Okay, so we basically have got events, and there are going to be two events. Okay, in one event we are basically going to have, you know, x, y and z. Okay, and this is actually going to give you the location. Okay, and then we have got the time. This is t. Okay. Understand this. Okay, this is not very difficult if you just understand it like a story, more or less. Okay, and then there is another event that is happening. Okay, and that is happening in the other frame of reference. So these two events, okay, are basically happening in the S frame. Okay, this is actually happening in the S frame. So if you do any kind of measurement on the S frame, it's x, y, z and t. Okay, and the other event is actually having the location coordinates as x dash, y dash and z dash, and time would be t dash. Okay, so both are time. This is in the S prime frame. So these are the two events that we usually have. Okay, so you have to consider this. So this is the entire situation, or this is the entire picture, and based on that we are actually going to do the Galilean transformation. Okay, so you know it's not very complicated, but then you know, since if I start now it will take some time to complete it. Okay, so we may not start it, but before that I'll just tell you one this basic idea. Transformation equation. So since I said Galilean transformation, so what we are going to do is we are going to derive a transformation equation. Some of you might have already done it before also. Okay, so transformation equation, so that's actually Galilean transformation. And what is this transformation equation? What exactly does it provide? What kind of information it holds? Okay, so this transformation equation is actually nothing but the relation between S and S prime. So if we are able to find out a relation between this S frame and the S prime frame in terms of what? In terms of x, y, z, t and x dash, y dash, z dash, t dash. That is called the transformation equation. Eventually, you'll see that if you are considering a normal velocity v, okay, this transformation equation is simple. But then if this velocity v gets comparable to the speed of light, Galilean transformation becomes invalid. Then we go into the concept of Lorentz transformation. So in the next class, what we are going to do is we are going to do Galilean transformation, okay, and going to build our ideas more on special theory of relativity. We are going to see that the Newton's law, okay, may be invariant, okay, in these kind of system, but if we are considering, let's say, Maxwell's equation, an electric field and a magnetic field, the Newton's laws might not be invariant.